All right, guys, today we got a beautiful problem. I tried doing this with some friends today and we were unable to solve it. I did some homework afterwards and I was able to solve it. Here is the problem. I'm gonna read it from my laptop, but I'll show it up here on the screen. We're just gonna read through the whole problem and do the setup. So it says, a block of mass, lowercase m, 2 kilograms, rests on the left ledge of a block of mass m, 8 kilograms. The coefficient of kinetic friction between the two blocks is 0.300. And the surface on which the 8 kilogram block rests is frictionless. A constant horizontal force of magnitude F equals 10 newtons is applied to the 2 kilogram block, setting in motion as shown in this figure here. If the distance L that the leading edge of the smaller block travels at a larger block is 3 meters, A, in what time interval will the smaller block make it to the right edge of the 8 kilogram block as shown in this figure? Note, both blocks are set into motion when F is applied. B, how far does the 8 kilogram block move in the process? Okay, so I think that's all I gotta read. I'm gonna go back to this when I need some numbers, but I spent some time thinking about this problem and here's what I've discovered. I'm also gonna show you guys a video right over here of what this kind of looks like. So here we have a frictionless surface along with a block, capital M, and then another smaller block with lowercase m. So this is the scenario. Then you push onto this block M so that this block M slides, but because there's friction right here, we should write coefficient of friction is equal to 0.300. There's friction between these two. Since there's friction, this lower block M, when it's pushed, it like grips onto this big block, capital M, and it slides the big block over. And over here, it is frictionless, so coefficient of friction equals 0. Also, what happens is, let's say we draw this little dotted line to mark the start of where the two blocks are. They're in line like this. After a specific amount of time, which we are looking for in part A, so this is the question we're looking for, the setup looks like this. So this is the original dotted line where the two blocks are lined up on. The lower block moves a little bit, right? But then the top block is lined up with this final edge over here after being pushed for some amount of time. So we apply this constant force of 10 newtons, right? 10 newtons over here. And we end up in this situation. And over here, we have pushed the block M, the capital block M, a little distance. I'm going to call this distance D subscript capital M. And then I'm going to call this distance from here to here, this is D lowercase m, right? So this is how much, if I give you this number, this is how much this block has moved. If I give you this distance, this is how much this block has moved with respect to this line over here, this dotted line which we've created with respect to the table. Another number they give you, which I'm gonna write in blue just to keep things a little bit split up here, is, let me just erase this guy. The distance from here to here is L equals 3 meters. So if the block is here, there's 3 meters left. Same thing over here, right? The block is moved to this side. This distance over here, the distance left on this M is also 3 meters, right? So it's asking us, how much time does it take for this block to move? So it took me some time to just think about this, read the problem over, and then write some stuff. I actually wrote some notes before writing the solution of everything that I thought of relating to this problem. I'll show you that a bit more in depth at the end of the video, but here's a quick run through on the side. And what I got to was, all right, we need to create a free body diagram for the two blocks individually. You might be like, oh, this is a system, but you actually have to do free body diagrams for the two blocks individually. So this is the problem setup, right? I'm doing it on a whiteboard, so it's very, very quickly thrown on here. But if you're writing it on a piece of paper, you want to draw as many pictures as you can, as many visualizations as you can, as many numbers as you can, so that this picture looks clean to you. Okay, so now I'm going to do lowercase m over here. What does the free body diagram of lowercase m look like? Here is the block m, right? It is being pulled down by lowercase m times g, right? Its weight force. The table, or this block, is pushing up on it with a normal force, right? If the force is canceled, the normal force is equal to mg. So that is everything in the y direction. I can't think of anything else. The block is also being pushed by 10 newtons. So I'm going to draw a vector this way. This is a force of 10 newtons. I'm just going to say 10 newtons. You can call this force anything. Force subscript P for pushing, anything you want, it doesn't matter. And there's also a force of friction, which I'm going to do capital F subscript curvy F subscript S, static friction. Doesn't really matter. This is the free body diagram for the small block. From here, we're good to go. So I'm going to draw a little line because underneath this, I'm going to do the big block, M. But before we get to there, let's just split this up and do some of Newton's law, second law in the y direction and the x direction. So in the y direction, we have the normal force pointing up, right, minus mg pointing down. That's why I put a minus sign there, equals sum of forces equals ma. Is the block moving up and down? In this situation, it's not. So acceleration in the y direction is 0. And from this equation, we can get n is equal to mg. And I'm putting a lowercase m over here because it's for the lowercase m block, all right? That is the y. I'm going to split this up over here and do the same thing for the x. So for the x direction, we have 10 newtons pointing in the positive x direction. Depends how you set up your coordinate system. In this case, this is positive. So I have 10 newtons minus this force of friction, minus force of friction. The force of friction is equal to mu s times the normal force, all right? Force of friction, coefficient of friction, which is given to us here, and the normal force, which you can pull out from this y component. So I'm going to put those two together, and it gives us mu s times m times g, and that is the sum of all the forces acting in the x direction. And here you get ma. There is actually an acceleration. The block is being pushed this way, right? So it's moving this way, its velocity is changing, its position is changing, so we have an acceleration. So I'm going to put lowercase m, a lowercase m, because we're splitting up the system, right? These blocks move differently, right? This block moves a greater amount of distance in the same time that this block moves a smaller amount of distance. So they move with a different acceleration. That's why I'm designating this m subscript lowercase a as the acceleration of this block here. From this, we can actually solve for the acceleration pretty cleanly. Actually, I did this over here very quickly. You guys can do it. Plug in 10 newtons. Mu s is 0.3. The mass of this block is 2 kilograms, and g is 9.81 meters per second squared. Do this. This, if you have it in SI units, gives you newtons. 10 newtons minus something, and then divide this m, which is 2 kilograms on this side. You have everything, and you just isolate for am. So here is a lowercase m. I did this calculation here on a little piece of paper, and I got 2.06 meters per second squared. This is an important number, the acceleration of the block. Why is this important? It's asking us how long it takes for this thing to move here. If we have the acceleration, we have the distance, and we have some other stuff, we can maybe use this to find how long it takes for this block to move. Cool. But before we get there, let's just do the same thing that we did here for this block. So now I'm going to cut off this, boom. Focus on the big block. So here's the big block. I'm going to draw it kind of large like this. The big block also has a weight force, but now it's capital Mg. Right? It's being pulled down by capital Mg. But it also is being pushed down by this guy. So the way the book answers this is there is a normal force of the small block pushing it down. And then there's the normal force of the table here. Since we have many normal forces, I'm going to subscript this normal force, capital M. It maybe looks a little bit weird here, sorry about that. Normal, capital M. Here's the normal force, lowercase m. Just look at this block, right? This block is here. It's being pulled down by its mass, but it's also being pushed down by the mass of this tiny block here. And we saw that this normal force of the top block is exactly equal to mg. So I can just put this mg here. This block is being pulled down by its own mass and the mass of this block. You guys might be wondering, like, when do I have to think about a system of blocks? When do I have to think about different blocks? In this scenario, we are creating one free body diagram for this block, one free body diagram for this block, but there is included information in this free body diagram which relates to this block. So you kind of have the system of blocks included in the free body diagram. Anyway, I hope that's okay. These are all the forces acting in the y direction. Normal force of the frictionless surface pushing the block up, mass of the block pushing it down or pulling it down because of gravity, and then the normal force of this thing pulling it down, or you can say the weight of this thing is the same thing. I'm actually going to put lowercase mg here. This thing is on a frictionless surface. There's no friction opposing it. There's no force pulling it this way. However, because we're pushing this block this way, and there is friction right here between these two blocks, this force of friction over here, this thing, this is the only force acting on this block, making this block slide this way. So look at my little video here. I'll put a little like picture-in-picture thing. This block is being slid this way because of the friction that this block is providing to this block. So the only force acting on this is a force going this direction, which I'm gonna call it force of friction. And because of Newton's third law, every action has an equal and opposite reaction, this force of friction is the same exact one as this force of friction. So it's mu s times normal, which is mu s times lowercase m times g, which I saw from my calculations was 5.886 newtons. So this is pretty important. This is the only force pushing the block this way, and it is only the normal force of this block. Hopefully that's okay. Talk about it with yourselves, leave a comment if this is confusing, but that's what I get. So now we have a free body diagram created for the big block. Now we can do the same thing here, cross this out, and let's do the sum of Newton's forces in the x direction. So in the x direction, we just have this 5.886 newtons. 5.886 newtons is equal to capital M AM. At this point, I can actually solve for the acceleration. So I don't even care about what's happening in the y direction. I can just isolate for this A and I'm chilling. So let me know if everything here is good. Please leave a comment, no stress about it. I'm just showing you guys the way I solved it. Okay, nice. So I'm gonna isolate for this A. AM is equal to, I have the mass of the big block, it's 8 kilograms. I move it on this side. Newtons and kilograms cancels to give you unit of acceleration, meters per second squared. And what I got here was 0.736 meters per second squared. So these are the accelerations of the blocks. Smaller acceleration for the big block and a smaller distance over the same amount of time compared to the smaller block having a bigger acceleration. So far, everything looks pretty good. And so far, all we've used is free body diagrams, some stuff about friction forces, and Newton's second law summed up into the y direction and x direction. In this case, I only did it in the x direction right here. If you want, you can do it for the y direction, see what happens, maybe some interesting thing we'll pull out of there. But so far we have these two numbers, this one and this one. I'm gonna erase everything and just write down these two numbers and this picture again, and then we're gonna see how we can solve the first part of the problem, which says how long does it take from this scenario to this scenario. So how long does it take for this block to be pushed all the way to the edge of this one? All right, here's what we have so far. This is the start of the picture. You apply a force just to the top block, giving it an acceleration of a subscript lowercase m, which is 2.06 meters per second squared. The friction between the two blocks also gives the bottom block an acceleration, smaller acceleration, it's heavier, whatever. This is the final picture you end up in, and I've drawn these extra kind of like distances. This distance L is the distance between the edge of this small block and the edge of the big block, this one here. This L is given to us as 3 meters, but these two aren't. So this distance, d lowercase m, is from the starting point here all the way to the edge of the small block. D for distance, lowercase m for lowercase m block. And then same thing here. D lowercase subscript capital M is the distance from this line here, where everything was lined up, all the way to the edge of this thing. Why is this important? We'll get to that in a second. Maybe you might have questions how I thought of this. I looked at the solutions, but then I also convinced myself that this is good. Looking at solutions is not a bad thing. So take a look at solutions if you are interested. So what is it asking us for? It's asking us for the time that it takes for from here to get all the way to here. What is the equation for position of these two blocks if they are undergoing a constant acceleration? You guys might remember this equation. So the final position is equal to the initial position plus the initial velocity times time plus 1/2 the constant acceleration times time squared, right? In this case, we're going to say both blocks start at xi equals 0. If we do that, then we can erase this entire thing. Also, once we start pushing the system, that is time equals 0, so the initial velocity is also 0, so we can cross this entire thing out. Now what we get is the final position, which I'm going to actually replace for this and this. So dm is equal to 1/2. I'm going to plug in the acceleration for the small m, 2.06 t squared, and then dm 1/2 0.736 t squared. I've now found the equations for the distances of these two blocks as a function of time, right, because of their accelerations. After this point, right, this block is going to fall off, so it doesn't really matter after this point in time. But right here, this is where we want to get at. And over here, you can see that this t is the only thing we don't know in this equation. Well, we don't know the distances, but we're looking for time for part A, so we can isolate for this. So it's kind of good that we have that as a variable. Now, this picture is important because it relates the two distances, this one and this one, which we have equations for, and this distance here too. So take a look at this. This big distance of the d lowercase m, this distance is created by adding this and this. So I can create a new equation by looking at this picture, which I'm going to put here. L plus d capital M is equal to d lowercase m. Right? Or you can think about it any other way. You can think about d lowercase m minus d uppercase m is equal to L. So just take a look at this picture, convince yourself that this is true. And this is a very important thing that we are going to use in the very next moment. We have this L as 3 meters, and over here we have functions for these two things. So I'm going to literally just take what I have here for dm, put it here, and then the same thing for the lowercase m, put it right here. So I'm going to do that right here. This is the equation we have. The only unknown here is time. Now we can isolate for time. What I'm going to do is subtract this onto this side, and I'm going to erase everything here. So I skipped a little bit. What I did was factor out a t squared from this entire thing, because there's a t squared here, t squared here. Factor that out. 1/2 times 2.06 is 1.03. 1/2 times 0.736 is 0.368. This minus this gives us this, and then I divide this whole thing onto this side so I can isolate for t squared. And by the way, 1/2 here and 1/2 here is unitless. This 2.06 was an acceleration with units of meters per second squared. This also was an acceleration meters per second squared. So this whole thing inside here, when we divide out on the other side, keep the units meters per second squared. This was a 3 meters. Meters over meters per second squared. The meters cancel and the second square goes to the top. So here we have seconds squared, and then we square root this to cancel the square over here and the square over here, and we get this fine answer, which is 2.13 seconds. So that's how long it takes from the block to get pushed all the way to the other side. This is the right answer. Let me know if you guys have any questions, any question at all. I got y'all. But try to follow this, try to do it on your own. And the second question is also quite easy after you know this. So it says, how long does let me actually read it out. It says, how far does the 8 kilogram block move in the process? So we found the equation for the position of the big block. It was just 1/2 times its acceleration, which was 0.736, and then times t squared. How long does the block move in this amount of time? We just plug in the amount of time that we found from part A in seconds, square that, and then we can get. So after plugging this into a calculator, 1/2 this acceleration, this time squared, canceling all the units, 1.67 meters. This is how long it travels. So as you guys can see, the main thing is thinking about how the problem looks. Like if you read the problem once, maybe you might have a confusion of what's happening. Creating the problem in real life, in this case, it was kind of simple. You have two objects. Let me know if you guys have questions. Thank you guys for watching. Please try the problem out on your own. This is an interesting problem. Here it is again. And also, I told you guys that I was confused with this problem. Here is a little tip for my problem solving strategy. I did this problem in class with some friends. It was difficult. We didn't know what we were doing, and we were also kind of rushed a little bit. So after that, what I did was find the problem. I just searched in the book at the back of chapter 5 on Newton's laws. I found a picture that looks exactly like what we had. It was a thing like this, a block, and then a block here. I'm like, this is exactly the problem. I found the problem. It's exactly the one that we saw, different numbers, maybe a little bit. And then I read the problem a few times, and then I wrote this in a little note just while sitting and drinking a little tea, trying to figure out what's going on. And then if you want to use ChatGPT, I copied my entire notes, put it into ChatGPT, put a picture of the problem, and I asked it, what's going on here? Is my process good? And ChatGPT started glazing me. It was like, you are doing amazing, good sir, amazing work. Maybe you will do a problem and it's going to say, no, you did something wrong here. I would be very hesitant with trusting ChatGPT or any kind of large language model, but you can use it to ask questions here and there. But if you have a problem and you don't feel like using ChatGPT or you don't trust it, I would say find a similar problem in the book and then find solutions to the book. Or check the book, see if one of the examples that you've done has something similar, do that example 1 or 2 times and then go back to this problem. And of course, share it with friends, ask your prof, ask your friends in the class, ask me, leave a comment, and I will help you out. And keep practicing, guys. Thank you for watching. Let me know if you want to see any other problems, and I'll see you guys in the next video.